In this video, we're going to talk about constitutional isomers. When you have a chemical formula, constitutional isomer basically are different isomers when the atoms are bonded differently. They have the same formula. For example, between ethanol and dimethyl ether, they both have the same formula of C2HCO and C2H6O. But in ethanol, two carbons are bonded directly and then followed by another hydroxy group. Whereas in the methyl ether, you have two methyl groups bound to the same oxygen. There's no bonding between the carbons. A similar type of isomers or constitutional isomers can be found in basically literally almost all of the organic molecules. For example, chlorobutane. If you have the chloro on the first carbon or chloro on the second carbon, they're both going to result into the same chemical formula, C4H9Cl, but the compounds are obviously differently because the chlorine are bounded to different carbons on the butane chain. Or a classic example would be even a pure alkane, such as pentane. You can have a linear structure or you can have branched structure, such as difference between pentane and 2-methyl-butane. They both obviously have the same formula, C5H12 and C5H12. Even with other more complicated functional groups, you can have constitutional isomers, like 2-propanol with a carbon-oxygen double bond in the middle carbon, or you can have a carbon-oxygen double bond or a carbonyl group on the terminal carbons. So here's an example how we should determine the different constitutional isomers given the same chemical formula. It's very important to remember the general binding pattern of all of the atoms, most of the atoms, such as carbon with 4 bonds, nitrogen with 3 bonds, oxygen with 2 bonds. Hydrogen and the halogens will possess only 1 bond only. So for example, when you have 3 carbons, 7 hydrogens, and 1 bromine, they can possibly have 3 carbons in a row, but the bromines can be replacing one of the hydrogens bonding to the carbon in the middle, or you can have the bromine bonding to the carbon at the end. They're both going to give you a very similar line structure with a propane chain, but with a bromine on different carbons. And of course, when you have bromine replacing the other hydrogen on the same carbon, does not give you a different structure. So make sure when you draw the constitutional isomers, don't duplicate the structures. Always examine after you draw a structure if two structures may look different, but they're actually the same structure. Of course, you don't want to miss any structures either. Now, when it comes to specific example, we need to learn how to draw the different structural base chain first. So for example, when you have 4 carbons, C4H9Cl, you might want to show, first of all, with 4 carbons, how many different possible way of bonding you can have. With 4 carbons, you can have 4 carbons in a row, or you can have 4 carbons forming this kind of a branched structure. And then on each possible structure, you can try to put chlorine on different carbons. Now here, by looking at the line structure, I guess it's not hard to see that between these 2 carbons on the end, the chlorine will show no difference. So for example, if you connect the chlorine on the right side of the carbon, or you connect the chlorine to the left side of the carbon, and it won't make any difference. What I'm trying to say is, you should see the identity, this exact same structure between the structure 1 on the screen and the structure below 1. So these two are exact same structure. Similarly, you can imagine between these 2 carbons, they are symmetrical. In other words, if you have the chlorine on this carbon or on the other terminal carbon, these 2 structures are exactly the same. So there are only 2 possible different carbons. I'm using triangle and circle representing them. So there are 2 possible isomers when you have the linear geometry of the butane. Now the second butane, which is branched version, there are 3 types of carbons. You can see there are 3 terminal carbons that are exactly the same, and then 1 more carbon in the center. So you can have chlorine attached to the center carbon, which maximize the 4 bonds of the center carbon, which may also indicate that there's no more hydrogen on the center carbon anymore. Now, on the terminal carbons, it doesn't really matter whether chlorine attached to this carbon, or even possibly the other carbon. These structures are the same thing. So with this chemical formula, you have 4 constitution isomers. Sorry. You can pause the video here, see if you can come up with some of the constitution isomers of C5H13N. Try to come out at least more than 10, even though there are possibly more than 10, 11 constitution isomers. In this case, you do want to keep in mind nitrogen can have maximum 3 bonds. Similarly, we want to show that there are possible structures with 5 carbons. We can have linear ones, we can have branched one, we can even have more branched ones. Now with the linear ones, we can have amines attached to the terminal carbon. We can have the amine attached to the second carbon. We can have the amine attached to the carbon in the center. You do realize that when you have amine attached to the next carbon, and that's going to exactly result into the same structure as the second one. Similarly, you can have amine attached to the next terminal carbon, which will be resulting into a structure same as the first one. So this one doesn't count. It's a duplicate. When you have a branched structure of 5 carbons, you can have the amine attached to on one of the terminal carbon, which you can imagine the bottom one will be the same. You can also have the amine attached to the tertiary carbon. You can also have the amine attached to secondary carbon. You can also have the amine attached to the terminal carbon. Just to keep in mind, you can't write nitrogen next to the carbon. You have to actually show the bond between the nitrogen and the carbon. With the more branched structure here, you can attach the amine to the terminal carbon, make sure you show the bond, or you can show the amine. Do you think you can show the amine on the central carbon here? The answer is no. Center carbon already have 4 complete bonds, so there's really no more space for the center carbon to have another bond anymore. So with the current drawing, we've already come up with eight isomers of C5H13 nitrogen. There are other possible structures because the these are all the examples of primary amines. We can also have secondary amine or even possibly tertiary amines. So, for example, we can have amine that's with a hydrogen and with another methyl group. If one methyl group is attached to nitrogen, then your base chain will not be C5 anymore. It's going to be only C4. So when you have C4, you have the possibility of 4 carbons in a row, or you can have 4 carbons forming a branch. Now, when you have 4 carbons in a row, you can have the amine with a methyl group. You can also have amine. That's a classic mistake that I didn't really draw the bond between the carbon and the nitrogen. So that's 4 carbons with a amine with methyl group attached to nitrogen. You can have the methyl amine attached to, again, sorry about this. Attached to the second carbon of the 4 carbon chain. With a branched structure, you can have the methyl amine attached to the terminal carbon, or you can have the amine attached to the central carbon. But the central carbon does have extra space for one more substance. You can even possibly have nitrogen with ethyl group. Now, with this kind of substance, now you don't have 5 carbons anymore. You would only have 3 carbons as the primary chain or base chain, which will result in only one possibility, which is 3 carbons in a row. Then you can have methyl with ethyl group substance on the nitrogen. Or you can even possibly have this, let me, just to save space. You can even have the 3 carbon chain, but the secondary carbon attached to the nitrogen. This nitrogen will have a hydrogen and the ethyl group on it. There are even more possibilities, which can be nitrogen with 2 methyl groups on it instead of hydrogen and methyl. And then we're still going to look at 3 carbon chain. When you have methyl group with nitrogen with 2 methyl groups, or the nitrogen with 2 methyl groups attached to the secondary carbon here. You may be asking, is it possible for nitrogen to have 3 carbon substance on it? So for example, is it possible for nitrogen to have not 1, not 2 carbons, with 3 carbons, like a propyl? And then attached to another carbon chain? Well, because we only have 5 carbons, so if nitrogen has more than 3 carbons attached to it, then that means nitrogen, the other group will be maximally 2 carbons. And that will be included in the possibility of this case, when nitrogen is attached to a 3 carbon chain with ethyl substance on it. So those are going to be the duplicate from the structure we already have. So far we've come up with 1, 2, 3, 7, 10, 16 of the different constitutional isomers. Now, if in the test there are more than 10 constitutional isomers, possibly we usually ask for a number that's not exactly the full. For example, in this case, as long as you can come up with 11 possible 11 possible isomers, you will get the full credits for this question.